Imagine an asteroid, barely a speck against the vast canvas of space, yet holding enough precious metals to make every single person on Earth a trillionaire. Sounds like science fiction, right? A fantasy ripped from the pages of a utopian novel? But what if I told you that this isn't just a dream, but a rapidly approaching reality, fraught with unimaginable wealth and geopolitical consequences that could shatter our current economic systems, spark new space races, or even lead to conflicts beyond our wildest imaginings? The truth about asteroid mining isn't just about gold and platinum. It's about rewriting the very foundations of human civilization. To truly grasp the monumental scale of what we're talking about, we need to calibrate our perspective to the cosmic. For centuries, our wealth has been confined to the finite resources of a single planet. Gold, platinum, rhodium. These are scarce, driving their colossal value. But out there, in the cold, silent depths of our solar system, billions of metallic asteroids drift through space like undiscovered treasure chests. These aren't just rocks. They're primordial relics, often composed of materials that formed before planets, rich in elements that sank to the core of Earth, making them agonizingly difficult to access here. We're talking about P-type and M-type asteroids, vast repositories of nickel iron, often laced with platinum group metals, PGMs like platinum, palladium, and rhodium. The sheer volume is staggering. One single, relatively small asteroid, perhaps just a few hundred meters across, could contain more platinum than has ever been mined in human history on Earth. Think about that for a moment. The total global supply of some of the most valuable resources we know could be dwarfed by a single space rock. This isn't just about increasing supply. It's about fundamentally reshaping the definition of scarcity. Our current economic models are built on the premise of limited resources, a premise that space mining could render obsolete, opening up a Pandora's box of challenges and opportunities that few are truly prepared to confront. But how do we know these treasures exist, and how would we even get to them? This isn't theoretical guesswork. Spectroscopic analysis from Earth-based telescopes and orbiting observatories has confirmed the metallurgic composition of countless asteroids. Missions like NASA's Psyche, targeting a unique M-type asteroid thought to be the exposed core of a protoplanet, are specifically designed to investigate these cosmic bodies, confirming their astronomical value. The technological hurdles are immense, yes, but not insurmountable. Companies like Planetary Resources and Deep Space Industries, though both now defunct, their foundational research lives on through other ventures, pioneered concepts like robotic prospecting probes, capable of identifying and characterizing target asteroids. Imagine autonomous spacecraft, equipped with advanced sensors, meticulously mapping a celestial body, perhaps even using small, localized drills to extract samples for on-site analysis. The next phase involves capture and extraction. This isn't about sending humans with pickaxes, it's about sophisticated robotic systems. One proposed method is the use of large, inflatable bags to capture smaller asteroids, then slowly bringing them into Earth orbit, or even to a lunar processing facility. For larger asteroids, the idea is on-site processing. Think massive solar concentrators focusing sunlight to melt the surface, separating valuable metals through techniques like fractional distillation in microgravity, or using high-powered lasers and chemical reagents to vaporize unwanted rock, leaving the precious elements behind. The refined materials could then be launched back to Earth, or more likely, used to build infrastructures in space, fueling deep space missions, constructing orbital habitats, or even terraforming other planets, creating a self-sustaining space economy. The implications for Earth are mind-boggling. A sudden influx of platinum could crash its market value to pennies, decentralizing wealth in ways previously unimaginable. Entire industries could collapse, while new ones focused on space logistics, refining, and manufacturing could explode. This isn't just an economic shift, it's a societal earthquake. What happens when the world's most valuable resources are no longer controlled by a few nations or corporations, but by whoever can reach them first in space? The potential for new space races, fueled not by flags but by fortunes, is very real. The ethical dilemmas are equally profound. Who owns these resources? Is it first come, first served? Should the wealth be distributed equitably among all of humanity, or will it exacerbate existing inequalities, creating an even more stark divide between the spacefaring elite and those left behind? These aren't questions for the distant future. They are questions we must begin to answer now, before the first trillion-dollar asteroid is brought within our grasp. The most valuable asteroids for mining are typically those classified as M-types or metallic asteroids. These are incredibly dense, sometimes composed of 90% metal, including iron, nickel, cobalt, and critically, a high concentration of platinum group metals, PGMs, such as platinum, palladium, rhodium, ruthenium, iridium, and osmium. Why are PGMs so important? They are crucial for catalysts in automotive converters, electronics, advanced medical devices, and even in many clean energy technologies. On Earth, they are extremely rare, found in concentrations of parts per billion. In certain asteroids, these concentrations can be orders of magnitude higher. For instance, the asteroid 16 Psyche, which NASA is currently exploring, is estimated to contain enough iron, nickel, and precious metals to value in the quadrillions of dollars, enough to potentially make every person on Earth a billionaire if the wealth were somehow distributed. This estimation typically uses current market values for these metals, which, as discussed, would likely plummet if such quantities became available. However, even with a massive drop in price, the residual value would still be immense. The methods for extraction are complex and evolving. Early concepts involved robotic spacecraft using advanced spectroscopy to identify specific compositions, then deploying modular processing units capable of in situ resource utilization, ISRU. Imagine a swarm of small robots acting like cosmic ants, methodically carving out precious metals. One highly discussed method for water ice-rich asteroids involves heating the ice to turn it into rocket propellant, effectively converting the asteroid into its own fuel station for return journeys or further exploration. For metallic asteroids, a more nuanced approach is required. Techniques like magnetic separation in microgravity, where different metallic components separate based on their magnetic properties, or even advanced chemical leaching processes within enclosed habitats, are being researched. Bringing these resources back to Earth itself is a monumental task, and perhaps unnecessary for much of the material. Instead, the focus is increasingly on using these materials in space to build large orbital structures, space habitats, deep space probes, or even entire lunar bases. This vision foresees a future where humanity is not just visiting space, but truly living and thriving there, fueled by the limitless resources of the cosmos. The timescales for this reality are shrinking. While full-scale mining operations are still decades away, the foundational technologies for identifying, characterizing, and even partially processing asteroid materials are being developed right now. Within the next 20 to 30 years, we could see the first significant returns from asteroid mining, potentially altering the global economic landscape irrevocably and presenting a true test of humanity's ability to manage unprecedented wealth and power responsibly. So, what does this truly mean for us? This isn't just about making a few rich people even richer, or even about creating wealth for everyone. It's about a complete reevaluation of our relationship with scarcity, with labor, and with the very concept of value. If raw materials become virtually limitless, the focus of human ingenuity could shift from extraction to creation, to innovation, to solving the grand challenges that plague our species. We could build space-based solar arrays to provide unlimited clean energy, construct vast orbital farms to feed billions, or establish off-world colonies as a safeguard for humanity's future. The potential for eliminating poverty and fostering an era of unprecedented prosperity is tantalizingly close. But with unimaginable opportunity comes profound responsibility. Who will control these celestial gold mines? Will it be national governments, powerful corporations, or a new international consortium? The answers to these questions will shape the future of our civilization, determining whether asteroid mining becomes a catalyst for global unity and a common human endeavor, or a new frontier for conflict and exploitation. To this day, the true implications remain an open question. The stars are beckoning, promising unimaginable treasures, but they also bring a mirror to our own humanity, reflecting our potential for both the sublime and the catastrophic. If you're intrigued by the mysteries of space and the forces that could redefine our future, the next exploration will delve into the strange disappearance of astronaut Nikolai Petrov, a Cold War enigma shrouded in secrecy and speculation.